Financial Modeling, Topic 15, Option Valuation and Hedging, Section 2, Simulating Stock Prices for Option Valuation. And this is going to be related to the next topic, in which we actually use a Monte Carlo simulation to value an option. Let's talk about simulating stock prices. One method to value options is to simulate stock prices using a random walk model and compute the present value of the average payoff of the call or put. So for example, if the payoff of a call is max 0 ST minus the strike, what I would do is I would simulate, say, 10,000 spot prices of the asset at the maturity of the option. And if I have 10,000 spot prices, I can get 10,000 payoffs of the option based on the random walk model. I'll take the present value of that to get back to today's dollars, and I would simply take the average of all 10,000 of those payoffs. Now mathematically we can write that as the sum from I equal 1 to say 10,000 of the 1 over 10,000, getting the average of the max of 0 ST minus a strike times e to the minus RT. Now we haven't used continuous compounding up to this point in the course, but e to the minus RT is simply a continuously compounded discount factor. So in other words, one way to, instead of doing this, is I could have just, instead of multiplying times e to the minus RT, I could just divide by 1 plus r to the t. In that case, the r would be a discrete interest rate. However, if I'm using continuous interest rates, I would multiply times e to the minus RT to take it to the present value. And we're going to use those terms because that's how our option models are generally reflected in continuous time interest rates. So we're going to write it that way. And then for a put, all I'm going to do is I'm going to change that to x minus st. So in these equations, st is the simulated stock price at the maturity of the option. I'm going to now show you in the next slide, we're going to be using risk neutral pricing for that. So what that we're going to talk about that spot price is going to be a little bit different than the one you've seen before. N is the number of the simulation iterations, say 10,000. R is the risk-free interest rate. And e to the minus RT, like I said, is the present value factor, which is equivalent to, say, multiplying times 1 over 1 plus r to the t. So let's talk about simulating stock prices. Now, we've used a formula like this before. The spot price at time t of an asset is today's spot price, S0, times 1 plus the expected return or mean return times t, plus that random z, what's that, standard normal random variable, times the standard deviation, and the standard deviation is scaled by the square root rule, so we take the standard deviation times the square root of t. So that's the equation we had used before. However, if we're talking about a stock with dividends, the difference is I take the mean minus the dividend. And so the way of thinking about that is a stock is the present value of all future cash flows. And if a stock pays a dividend, that dividend is factored into the cash flow. However, once a stock pays a dividend, the value of the stock price will fall by the exact amount of the dividend. So if we're just modeling the stock price, we want to subtract, if mu is the expected return of the asset, the actual price is reduced by that dividend yield D. So this is a way of modeling the stock price, not just the total stock price for a non-dividend payer. Now, I will show you in earlier models when we talked about portfolio simulations, even though I was looking at portfolios that paid dividends, I still used this formula. Now, the justification for using this formula for a dividend payer is you're not really trying to simulate the asset price. You're trying to simulate the total return of the asset, including the dividend. So in this case, when I didn't subtract out the dividend yield, I was implicitly assuming that I'm reinvesting the dividends in buying more stock. So I would use this formula if you're trying to simulate, say, a total portfolio return, like I did for that financial planning model. However, if I'm simulating the simple stock price to value the option, I'm going to subtract off the dividend. If I was going to do this model here in continuous time, in other words, continuous compounding, I would take the current spot price times E, that mathematical constant E, to the U, expected return, minus the dividend yield times T, plus my random Z times sigma times the square root of T. However, the formula we're going to use is going to be this one right here. And the only difference, it has one more factor right here. And that is, I'm going to simulate the spot price by taking today's spot price times e to the minus the dividend yield minus 1/2 the variance is an adjustment factor I have to use for my factor or for my simulation on the pricing of options, times my t times my random z sigma times square root of t. Now, one question is going to come up is this r is no longer the mu. In other words, I'm simulating the stock price based on r, which is a risk-free rate. Why would I assume that stocks go up by the risk-free rate? Well, I wouldn't. Normally, I'd say they go up by the risk-free rate plus a risk premium given to me by CAPM. However, when valuing options, it is perfectly okay to assume that stock prices go up by the risk-free rate as a computational shortcut. And what we call, when we do that, we say that we're assuming risk-neutral pricing. So if you're assuming stock prices go up by the risk-free rate, we talk about that being risk-neutral pricing of options. And as it turns out, the only reason we do that is because it's just easier. Why insert another model, say CAPM, to get the expected return when it turns out that we can, for the purposes of valuing options, we can assume the risk-free rate, and that risk premium kind of cancels out in my valuation of the option. So that's an important concept here. I'm simply assuming stock prices go up by the risk-free rate as a computational shortcut for valuing options. I don't really think that stock prices will go up by the risk-free rate. And that's it. That's the model. This formula is the one we're going to use to model my 10,000 possible stock prices. And then I'll use a Monte Carlo simulation to calculate the average payoff. So that'll be the next topic.